A modern autonomous robot can show perfect signal strength, optimal RF conditions, and maximum physical layer data rates, right up until the millisecond. It misses a critical command and halts its entire operation. Telecommunications providers are deploying massive physical layer upgrades. We have 5G Advanced and Wi-Fi 7, introducing multi-link operation, wider channels, and enhanced modulation. Yet interactive AI, cooperative robotics, and vehicle-to-everything workloads still regularly fail to meet their response deadlines in the field. The disconnect comes from how we measure success. Network engineers typically optimize for high capacity and low median latency, the P50. But an average latency of 15 milliseconds provides no security for an autonomous vehicle if a sudden interference burst pushes a single sensor fusion update past its limit. Autonomous network health is dictated entirely by tail latency. The 99th percentile, the P99, measures the slowest 1% of network interactions. For a robotic control loop or a safety advisory system, survival depends on capping that maximum delay. A low average means nothing when a routine cell handoff, a sudden compute queue, or an unexpected model fetch causes a 50-millisecond spike that breaks the application sequence. A high-capacity radio link is necessary but insufficient. Wireless AI performance is determined by an entire coupled sequence of systems, not an isolated air interface. This diagram illustrates the full wireless AI service chain. Notice how a signal begins at the endpoint, a vehicle or camera, travels across the 5G or Wi-Fi radio access network, and reaches the initial access edge. Delay compounds at each step. The journey then continues across downstream hops. The packet enters the transport layer via Ethernet or SD-WAN, waits in an edge compute queue for an AI accelerator, and fetches state from a core cloud database. A localized delay anywhere in this sequence triggers a failure at the end. A perfectly transmitted radio packet is useless if it arrives at an edge node with a cold AI model, or if a massive background video upload saturates the return path. Wireless AI is an end-to-end systems problem. The solution requires time aligning the radio schedule with the downstream transport path, the available edge compute capacity, and the specific application deadline. To bridge these isolated domains, the infrastructure requires an out-of-band coordination overlay. This is the exact role of the Predictive Tensor Control Plane, or PTCP. Total end-to-end latency is an additive chain of events, broken into two categories. Unavoidable structural constants, like propagation delay, RF limits, and mandatory compute, cannot be optimized away. Addressable delays are coordination-dependent. Repetitive retries, downstream queues, wrong edge routing, and AI wait times. This brings us to the Amdahl bound of networking. You cannot mathematically optimize a system beyond the limits of its fixed physical requirements. No scheduler update will repeal the speed of light or the mathematical limits of Shannon capacity. PTCP does not try to rewrite those physical laws. It exclusively targets and compresses the addressable coordination delays. This graph plots the direct relationship between removing coordination delay and reducing total latency. If 40% of a baseline is coordination dependent and the control plane removes half of that delay, the system yields a 20% direct reduction. Funneling capital exclusively into new radio hardware yields diminishing returns because it ignores the largest, most addressable source of friction in the AI service chain. Coordinating these disparate domains creates a strict architectural challenge. How do you align a 5G cell tower, an enterprise router, and a Kubernetes cluster without introducing an invasive proprietary air interface? The PTCP architecture answers this by deploying as an overlay, beginning with the observation plane. This layer correlates time-stamped telemetry across multiple existing standards, pulling radio indicators and incorporating host-level kernel telemetry. The observation plane tracks edge cache freshness, downstream path telemetry, and application deadline outcomes alongside traditional RF health. This synchronized cross-domain visibility is the absolute prerequisite for predictive control. You can only prevent a queue buildup if you can see the upstream demand and the downstream capacity simultaneously. Telemetry feeds the predictive slow path, forecasting near-future risks. The policy and safety gate then checks proposed actions against carrier rules and application authority. Once verified, instructions move to the bounded fast path, executing via existing interfaces like 5G QoS. This introduces a sharp, non-negotiable architectural distinction. PTCP is strictly a coordination overlay. It never overrides the native hardware logic. The base station or access point retains absolute control over scheduling the air interface, and the application retains complete ownership of safety semantics. The overlay exists to provide topology-aware intent, ensuring that the correct flow arrives at the correct edge resource, exactly when needed, without micromanaging the radio itself. Applying remote network control to a physical environment introduces severe operational risk. If a communication failure occurs, a heavy industrial system cannot wait on a cloud server to tell it what to do. A cooperative robot requires immediate, autonomous physical braking. Therefore, PTCP enforces a strict rule. A remote network controller can never home safety authority. Local failsafes, middleware semantics like ROS2, and the system's defined operational design domain remain the ultimate authority. If the control plane loses its connection, if its predictions go stale, or if an API fails, the failsafe mechanism triggers. All network actions immediately expire, and the endpoints automatically default to their validated local safe states. The network overlay acts as a force multiplier to optimize supporting data. But by design, the loss of the network never removes a machine's ability to protect itself. Modifying a complex, multi-tenant network environment requires extreme operational discipline. The system cannot simply be switched on in production. Integration follows a mandatory, 4-phase, evidence-gated adoption roadmap. Phase 1 covers the first 30 days. This is a strictly observe-only baseline period. The system maps the service graphs, identifies network deadlines, and time synchronizes telemetry across the infrastructure without taking any action. Phase 2 introduces the shadow mode. Predictions run against live data to calibrate counterfactual policies. The system calculates what it would have done and verifies if the logic is sound, still without altering traffic. Phase 3 is the canary deployment. The system applies reversible quality of service actions, starting exclusively with non-safety bulk traffic, utilizing tight expiry limits and one-command rollbacks. Finally, Phase 4 expands to certified, scaled profiles. But expansion only occurs if the system passes strict, pre-registered non-regression gates. In modern network engineering, a performance gain is categorically invalid if it is purchased by starving an unmonitored tenant, changing an application's output, or suppressing a critical safety message. Massive physical layer capacity upgrades routinely fall short of their performance targets because the variables surrounding the radio remain entirely uncoordinated. PTCP bridges the gap between the speed of the physical link and the actual demands of the application. PTCP provides the predictive intelligence required to orchestrate native wireless and compute mechanisms across infrastructure boundaries. Aligning these domains ensures that AI responses arrive before their deadlines expire, cooperative perception systems receive fresher telemetry, and robotic missions operate with predictable stability. By managing the addressable delays across the entire service chain, the control plane turns variable, unpredictable wireless access into a resilient, deadline-aware edge-to-cloud execution fabric.